Hi, boys and girls. All right, I'm getting ready to make a graph for the data that we collected in the previous video when Nick was doing a slow walk and trying to stay at the exact same speed. Remember that if you're staying at the same speed, that's called a constant speed. And in our last videos and on Monday, we learned that walking at a constant speed makes a diagonal line. So I want you to see what it looks like when you are walking really slowly and how the diagonal is different from when you're walking um, fast or medium speed, right? All right, so we'll compare the three at the end of this video too. All right, so I already have the whole graph set up for us just to save time so the video is not so long. But remember that every graph has a title. We're working with the x-axis and the y-axis. We've labeled the x-axis with distance in meters and with time in seconds. And it's critical that you always label your graphs axes because otherwise people won't know what the data is about. All right. And then, of course, the title gives you the main idea of the graph, which is just like in literacy when you're trying to find the main idea of a passage. Now, I made the data table with the time first because, as I said before, the time is always going to be what's graphed on your x. Oh, I made my axes wrong, babies. I just realized I made my y-axis here and my x-axis here, and that is not correct. So note, I'm fixing that right now. Sorry, right? Yes, this is always the y-axis and the x-axis is always on the bottom for time. All right, so now when you're trying to take your data table and turn it into coordinates, keep in mind that each coordinate always starts with the x, and x is time, and the second coordinate is the y, which in this case is distance. And remember, we're making a line graph, and line graphs are good to tell things that happen over time. All right, so our first coordinate is when Nick was standing at the zero graph card, and also no time had passed. So our first coordinate is zero distance and zero time, which is right here at the very corner of the graph. All right, next, let's go and make our next one. Our next coordinate is 4, 1. At 4 seconds, Nick was only 1 meter. That's pretty slow. All right, the next coordinate is 7, 2. At 7 seconds, he had only gone 2 meters. The next coordinate is 10, 3. At 10 seconds, he had gone 3 meters. And the next one is 13, 4. It took 13 seconds for Nick to go just 4 little meters. All right, the next one is 15, 5. It took 15 seconds for Nick to just go 5 meters. And next is 18 and 6. It took 18 seconds to go 6 meters. So he was walking really slow, y'all. All right, the next one is 20 and 7. He sped up a little because it only took 2 seconds to go a meter. And the next one is 22, 8. So he sped up just a little bit there at the end. All right, and now let's graph our coordinates. All right, the first one we already did is 0, 0. Remember that the first coordinate, you go to the right because you got to crawl before you can climb, right? So the first coordinate is the crawl over coordinate. We already did 0, 0, so we'll crawl over 4 and climb up 1. Crawl over 4, climb up 1. And keep in mind that I'm making my point on my graph right where the two lines intersect, not in the spaces, but right where the two lines intersect. All right, my next one is 7, 2, so I'm going to crawl over 7 and climb up 2. My next one is 10, 3, so I'm going to crawl over 10 and climb up 3. All right, next I'm doing 13, 4, so I'm going to crawl over 13 and climb up 4. All right, the next one is 15 and 5. So I'm crawling over to 15 and climbing up to 5. And then next is 16, no, 18, 6. So I'm crawling over all the way to 18 and then climbing up to 6. And then 20 and 7, crawling all the way to 20, climbing up to 7. And last is 22, 8. I'm going to crawl all the way to 22 seconds and I'm going to climb up to 8. Now, if I connect these are not making a perfect diagonal, but this is coming out probably the best out of any of them. So I'm going to kind of make it go right through the middle so you can kind of see how the diagonal would form. If Nick was able to perfectly walk in a perfect constant speed, and if I was able to be perfect in my capturing of the time that he passed the card. So this one would be slow constant, and I would like for you to compare the graphs. Let me lift this up. All right, do you notice that the medium constant speed is not as flat as the slow constant speed? Okay, let me see if I can make this a little bit less blurry, a little sharper. That's a little hard to do. All right, so do you notice that the slow constant is kind of flatter and then the medium constant is a little steeper of a slope? Right? Think of it as a ramp, right? And in science, I mean, in math and science is literally called a slope, like the slope of a hill. When you're doing the slow constant speed, your slope is flatter. And when you do the medium constant speed, your slope is a little bit steeper. And now let's compare the fast constant slope to the slow constant slope. Look at the slow constant. Here, let's see if I can make it a little bit higher up so you can see more of it. So it can compare the slow constant walk to the fast constant walk. Also, you can see that it took 22 seconds for Nick to go 8 meters in the slow constant walk, whereas in the fast constant walk, it only took him 7 seconds to go 8 meters. So when you have less time that you take to go the same distance, it makes the angle or the slope of the diagonal much steeper, and that always indicates a faster speed. Feel me? All right. When Nick went slower, it took 22 seconds to just go 8 meters, and that made the slope of the line way flatter. All right, that's another good one, y'all. I'm getting ready to do one last graph for today, and then you'll have a short Google form, and then you'll be done for the day. I hope you're learning. I hope you're watching every video. Love y'all. Beat it.